All right, right. So yeah, I'm Zach Yedidia, and I'm gonna tell you about running bare metal smart contracts with this project called Deterministic Client. Um, so to start, I'll lay out like sort of the two combined pillars that we're gonna try to put together in this project. So on the one hand, we have like blockchain systems that rely on replicated state machines as the fundamental mechanism. And one of the key properties that replicated state machines rely on is determinism. Now, on the other hand, in the design of like powerful computing systems, we like to have extensibility, and we see this in a lot of different forms of systems. So, like in your web browser, you have extensibility in the form of JavaScript. Maybe in like games, there's extensible systems provided with Lua, and then on blockchains, we have smart contracts where there's like an extensible a language to modify how the system works. And for enabling extensible systems, what we need is sort of a sandboxing approach so that we can run these little plugin programs that are going to extend the system in a safe and secure way. And so this talk is going to be about sort of combining these two things, and particularly how to design extensible blockchain systems that are performant and efficient. So going a bit more into the extensible blockchain systems and how smart contracts work, some of the properties we need to enforce with our sandbox when we run smart contract programs are that they're isolated from each other, they're preemptible, so they won't run forever and take over the processor, and they have to be deterministic. And so combining these three properties together leads to kind of a an interesting systems design question and how to do this well and efficiently. And so existing smart contract systems have execution environments for running smart contracts that rely on language virtual machines. So like there's the Ethereum virtual machine, or maybe you run your program as like a WebAssembly program in the WebAssembly virtual machine. Um, and so let me tell you a bit more about what the sort of trade-off is in this type of execution environment. So normally, when you run a program, you just compile it as native code. You use like LLVM, which is sort of a state-of-the-art compiler, to turn it into machine code, and that's going to run directly on the CPU. That's like your typical program. But this is very unconstrained. You can't really, it's difficult to enforce the properties that we need to enforce with sandboxing, namely like preemption, determinism, and isolation in this environment, because you're just getting sort of raw machine code out of the compiler about which is very hard to reason. Um, so typically we use language virtual machines where you define like an abstract machine that has the properties that you want. And then you compile to that abstract machine. And this allows you to have like this constrained environment. But typically the way that you execute the programs for this abstract machine are slow. And so this trade-off in performance leads to a difference in how much gas fees cost. So the performance is directly tied to the gas fees, and like this can cause issues for running some certain like CPU bound algorithms and smart contracts. So I have some examples here of like basically algorithms that use a lot of heavy cryptography tend to maybe cost like impractical amounts in terms of gas fees because the execution layer is slow. And so by not using like the native code, we're sort of leaving performance on the table. And there's a question of like, can we recover it? So let's look a little bit deeper at how these execution environments work. So on the left, we have like the native execution environment where you're going to take your source code, for example, a C program, and just compile it with with LLVM or a state-of-the-art compiler down to machine code directly. Um, on the other hand, in a language virtual machine environment, you're first going to compile, for example, using LLVM still, but you're going to compile to that abstract machine representation, so like a WebAssembly program. And then to actually run it on a computer, you need another stage to turn it into machine code, something actually runnable. And typically, this layer is implemented as either an interpreter or a JIT compiler. And so interpreters are like maybe the standard in blockchain smart contract systems because they're simple to implement and it's easy to reason about their security or easier to reason about their security. But they have a really sort of large slowdown factor because they're like manually executing each instruction in the program and sort of simulating this abstract machine. A JIT compiler, on the other hand, is going to compile these instructions directly to the machine code, but you're still going to get some slowdown And these programs are typically very complicated, and so there's this trade-off between the complexity, the security, and like how efficient you can go. You can add more complexity to get maybe a faster compiler uh, or faster generated code, but this comes at the expense of more chance of issues and bugs and security issues coming up in your execution environment. Um, so the question we're going to try to answer in this project is like, why can't we just directly run this native code output from LLVM? And the answer is like, we can do that with some restrictions, and we can recover mostly near native performance when we do that. So the four main problems that come up when you try to run just like machine code that comes out of LLVM in a smart contract and try to enforce the properties of isolation, preemption, and determinism on those programs, these four categories that I've laid out here. Now, the first category, this runtime API, is like, in a normal program, it can access the system clock, it can access all sorts of things. So we're going to say like, this is sort of handled for us in terms of the program. We're going to run in a constrained environment, which I'll explain, but like the operations exposed to that program are going to be deterministic operation, a deterministic API for it to call out to the host. So there's no parallelism, none of that. And this is just consistent with other smart contract execution engines. We can just reuse their API that they provide to the abstract machine programs. The other problems that I'll tell you about are and how to solve them are going to be like things like hardware instructions and the non-determinism that can come up in those. How to do preemption, specifically how to do it deterministically. Normally when you preempt programs, you use timer interrupts, and that's not deterministic. So we have to do something special there. And then if we have multiple programs, multiple sandboxes, how do we ensure that the like visible addresses to them are deterministic? In these typical sandboxing programs, you would load sandboxes into the same address space, and they would get different addresses, and then they can view the differences in those addresses depending on where they're loaded, and that can introduce some non-determinism. And so we'll also talk about how to deterministically restrict the visible addresses so that it's always the same. Okay, and the system overall is called Deterministic Client. And so this is just an overview of what we support and the sort of broad architecture. I'm going to talk mostly about the x86-64 implementation in this talk, but we also have an ARM64 version. It's important to note that like these are separate. So one of the trade-offs we make with this type of approach is that it's architecture specific. So with like an abstract machine approach like WebAssembly, you get some more portability across different architectures. Here we're gaining our advantages in terms of performance by also sort of specializing to a particular architecture. And the overall architecture of the system looks something like this. So you're going to take your C source code, and then when you compile it with LLVM and apply some rewrites to the assembly code that gets generated. And these rewrites are going to allow the program to pass a verification stage. So once the program is generated, you have a runtime environment that's going to load and run it. And before it accepts to run the program, it's going to run this verifier on the machine code, and it's going to prove to itself that like the properties of determinism, preemption, and isolation hold before it actually agrees to run the program. And this verification has to this is the like trusted component of the system, right? So we want to keep the verifier small, so it's like less than 1,000 lines of code, and then also it needs to, we're going to need to change how we generate these assembly instructions so that the verifier can prove to itself. So the verifier is sound and can prove to itself that yes, indeed, like these properties hold. And there are some cases where like a program might actually have these properties, but the verifier can't prove to itself that it does have those properties, and so it'll just reject those programs. Okay, so now I'll go through a little bit. So dealing with that first problem of there are some instructions that are non-deterministic. How do we restrict the instructions in a program to some deterministic subset? So we basically see that most programs use programs mostly use a core subset of deterministic instructions. These are things like arithmetic instructions, logic instructions, and control flow. And so here's some example program. It like moves a number into a register, then it adds two registers together. It just does some operations, and these are all deterministic. The CPU instruction set defines clearly what these instructions are going to do. And so we can have our verifier sort of look at each instruction and say, okay, this move instruction, I know that move instructions are deterministic, so that looks good. This add instruction looks good. The and instruction looks good. And then like if it does this for the whole program, it can be convinced of that the program is deterministic. And if it sees some instruction that's not within the subset, it'll reject the program. So there's a problem though, which is jump instructions. That's a common thing in like general purpose programs. But in x86, these jump instructions prevent sound analysis. And the reason for this is the actual like encoding of the program and the instructions. So when you turn this program into like a set of bytes that can be executed by the CPU, there's some encoding here. And so these are like the bytes that correspond to this program. And if we have a jump, what we can do is we can like load the address of these bytes into a register and then jump to it. And so we're going to jump to these bytes, and these bytes actually represent like a completely different instruction that could do something non-deterministic. And so these indirect jumps can jump into the middle of another instruction and cause some non-determinism to occur, basically executing some instruction that our verifier did not see, right? It's like another instruction embedded inside of the encoding of this move instruction. So in order to have sort of sound machine code analysis, the first thing we're going to do is going to be to enforce aligned bundles on the machine code. So we're going to say the rules are no instruction. So we're going to organize our instruction bytes into 32-byte bundles and say no instruction may span a 32-byte boundary, and then all jump targets must be 32-byte aligned. And what that means is basically like all the jumps are gonna go to some 32-byte boundary, and there may never be an instruction spanning that boundary, right? So it can never go into the middle of an instruction. And so when we analyze, we're going to be looking. This is not, the move is a deterministic instruction. That's good. The LEA is also fine. But then the jump, we don't allow jumps on their own because this jump may arbitrarily go anywhere. So instead, we only allow a jump if it's followed by an AND instruction, which is going to set the target to a 32-byte boundary. And that guarantees that this jump target is going to a 32-byte boundary. And the compiler has to produce a program where like all the jump targets go to 32-byte boundaries, and like and then all the jump instructions have this preceding AND instruction for the verifier to allow this jump instruction to occur. And so if we always have this AND beforehand, we never allow an instruction to span a 32-byte boundary, then we know that it's impossible to jump into the middle of another instruction and execute some unanalyzed instruction. So once we have aligned bundles, we can like soundly analyze the machine code program and categorize all the instructions within it and make sure that they're all within some safe subset. So another issue on x86 is that some instructions they set the flags register. There's like a hidden flags register which contains like zeros and ones. And certain instructions can put the flags into an undefined state. It can set one of the bits in the flags register to an undefined value. And this undefined value, in practice, it is actually 0 or 1 on any particular CPU. But on like different CPUs, like an AMD CPU versus an Intel one, those will actually have different values if you execute that program. And so that program will behave non-deterministically if you execute it on different x86 CPUs. And so this is an example. The div instruction, the x86 specification says that all flags are placed into an undefined state. And so if we have this program that like performs a divide and then tries to jump based on the 0 flag, this program will do different things on different x86 CPUs. So we need to have our verifier, be able to reject this program. And basically, it needs to be able to see that like whenever a flag is read, it must be in a defined state. So in order to do this, we have two cases of sort of we want to say that like when you enter a basic block, you only ever if you ever read a flag, you have to have set it to a defined state beforehand. And so we're going to say on the one hand, for indirect jumps, we don't have to worry about indirect jumps because there's always this AND instruction beforehand, and AND puts all flags into a defined state. So the important thing is like we can do a data flow analysis of the static basic block since we don't have to worry about the indirect jumps. And so we just are going to see like if there's a jump that reads the 0 flag in the same basic block, there has to have been like an instruction that sets the 0 flag to a defined value. And if that's the case, then we can accept the program. If we don't see such an instruction, then we reject the program. In certain cases, The compiler, like LLVM, will actually compile programs where like it will set the flag in one basic block, and then it'll do uh, a jump, and then in a different basic block, it'll read that flag. So our analysis supports up to one basic block away. And then LLVM never tries to set flags across like two basic blocks away. So the analysis can just be conservative and do this one basic block away search. And then if it doesn't, and that handles like basically all the programs that LLVM will generate. So those are like the programs that we actually want to run. So there's a few more cases. So there's things like shift instructions, things like invalid prefixes on instructions. So the paper has a bit more details on some of these other cases. But basically, like these are just part of the restriction to the safe subset that we want to perform with our sound machine code analysis. And so in the end, we get like roughly, you can get like 100 to 225 instructions, depending on whether you want to include like certain SIMD instructions. So 225 is like the larger choice of subset. 100 is if you just choose like core integer and logic operations. And yeah, so that's what the subset roughly looks like. Okay, so that handles our hardware instructions. Now we'll talk about the, the the preemption problem. And there are two approaches we're going to use here. There's something called branch-based metering and then timer-based metering and optimization on the first one. Okay, and then after that, I'll tell you about this position oblivious code approach for handling multiple sandboxes. So, okay, um, with preemption, we would like to use timer interrupts or something, but we can't because that's not deterministic, right? The timer interrupt could fire to preempt the program at any time, and so it could happen after or before like some sort of side effect that the program has by calling, if the program calls like some API function to do something to the host system. Then if that program runs multiple times or on different machines, that timer interrupt may fire before or after that side effect occurs. So we need to do some sort of software-based tracking. So what we're going to do is we'll just keep an instruction count of how many instructions remain before we preempt the program in a register, R12, for example. And then we want to exit the program or force the program to exit when R12 becomes negative. So our verifier is basically going to look at like and it's sort of a verifier compiler working together. The compiler is going to insert some instructions at the end of every basic block that are going to update R12. And then the verifier is going to, when it reads the program, is going to make sure that those instructions exist. And so what this is going to look like is we have some basic block where like some jump enters the basic block at the top. There's some instructions that execute to do some computation. And then at the end, we update our R12 gas counter. So we reduce the gas by the number of instructions that were in this block. And then if it's negative, we execute a trap instruction. So doing this has like a very specific sequence that is more detailed in the paper. But basically, yeah, we can force the program to exit and be deterministically preempted using this mechanism. If an indirect jump arrives somewhere in the basic block, that's actually fine. It'll just get overcharged for additional instructions. The point is that it can't arrive in the middle of this sequence because this sequence of instructions fits within a bundle, and the indirect jump must always target the beginning of a bundle. So it can't skip over the check, for example. Okay, so now timer-based metering is sort of an optimization on this, where we're going to delete this. The expensive part of branch-based metering is this check that we do, because this has like a conditional branch inside of it. And so we want to delete that entirely. We're just going to track now the gas count in R12. And then we'll use a non-deterministic timer to help us. And then uh, when there's an external call or side effect, we'll check the gas, and when the timer fires, we'll check the gas. And if the when we check when an external side effect happens, and we check and we see that the gas is negative, we're actually just going to terminate the program then. And this means that like even though the program may continue for some amount of time after it runs out of gas, it'll never be able to like externalize any side effect that it has during that. So it's still like deterministic from the external view in terms of what side effects this program has. So finally, I'll tell you about the multiple sandboxes thing, which has to do with when you're running Decal with software-based memory isolation, which is what we want to do when we want like very fast startup time for the sandboxes. Um, so we want to have, because we don't want to make like a separate Linux process for each sandbox, we want to actually spawn each one inside the same process. And so we use software-based memory isolation for this. This is built on top of another project of mine called LFI. And the approach is basically we have like a 4 GB region for the sandbox, and then we're going to rewrite the loads and stores. This is the same like verifier compiler approach, so that the loads and stores are always expressed as 32-bit pointers from the base of the sandbox, and therefore they're always constrained into this 4 GB region. But there's this problem when we do this, which is that like these addresses, normally LFI just allows you to view the base address of the sandbox or um, like the arbitrary addresses within the sandbox, like the stack pointer, for example, which is also going to point somewhere in here. Or like you use a call instruction, and that call instruction pushes the return address of your function, of your calling function or your calling instruction onto the stack. So then it can just observe the return address. And these full addresses are different depending on where in the address space the sandbox is loaded. The base will be different. And so that is a form of non-determinism that the program can observe. Um, and so what we want to do to prevent this form of this information from leaking through is basically to never allow the sandbox program to read the top 32 bits of a pointer, right? Because every offset from the base is deterministic. It's always, no matter where the sandbox is loaded in the address space, these offsets within the sandbox are the same. It's just like the top 32 bits of every pointer that get changed based on where it's loaded in the address space. And so if the program can't read those top 32 bits, then then it'll be deterministic with respect to where it's loaded. So we're going to disallow reading from RSP. So ESP is the bottom 32 bits of RSP, which is a 64-bit value. And so ESP can be read, but RSP cannot. And then also like use of a call instruction is disallowed. And so instead our compiler is going to generate instructions that look like this. And the verifier is going to, for example, the verifier will reject any program that contains a call instruction. It will only accept programs that use sequences like this to perform calls, where like it manually pushes a 32-bit push L, pushes a 32-bit address, and then it uses a jump instead of a call. And similarly for like accessing the stack, it accesses through ESP instead of RSP. So I give a short digression about LFI, which I mentioned earlier. But yeah, this is a project that I've been working on, just does the isolation portion. It doesn't do like the preemption and determinism. And it's currently in the process of being upstreamed into LLVM. So it might be available, or it'll be available soon for like you to use in Clang, and sort of that's also the it's a foundational part of the Decal approach as well. And so if Decal becomes something that is broadly used, there's also a path towards larger adoption in terms of LLVM support. Okay, finally I'll talk about the evaluation. So here's some benchmarks from running on spec and specifically comparing against Wasm time. So Wasm time is a JIT compiler. I have some comparisons with an interpreter later, but basically the interpreter is so slow in these comparisons that it's not worth including in the graph. Um, and here's what the overheads look like compared to native code. These are like percent overhead compared to native across a variety of benchmarks. So the decal HW is just the enforcement to make sure that the instructions are within the deterministic subset, but it's not enforcing preemption and it's not enforcing isolation, software-based isolation. It's sort of assuming that maybe you have some sort of hardware-based mechanism for enforcing isolation. So this is just the cost essentially of the bundles and like some rewrites to make all the instructions deterministic. Then we have like a comparison with what just like this is isolation on its own without determinism. And then here we have a number of mechanisms which provide the deterministic and software-based mechanisms that we want. So with position oblivious code, but no preemption, it's roughly the same performance as LFI. And then once we add timer and once we add a metering approach, we lose more performance, but up to a limited amount. And then WASM time, this is WASM time, the JIT compiler, without any preemption. So fuel is the preempted version, and then WASM time is just like providing, it's sort of the equivalent of decal LFI with position oblivious code. It's providing determinism and isolation, software-based isolation, but no preemption. And then fuel is the preemption version. And so we can see also, yeah, sort of the comparison between these various approaches. Finally, I also have like this comparison on a more blockchain specific workload with the zero knowledge virtual machine, zero knowledge proof verification. And here, we're again seeing similar results where like the WASM time is roughly like 2x worse than native, where Decal is only, 10 to 30% worse. And then WASM 3 is an interpreter, and here we're getting like 30 times slowdown compared to native for running these basically advanced cryptographic routines that are doing zero knowledge proof verification. And then we also evaluated on Groundhog, which is a highly parallel smart contract engine. And this is sort of benchmarking these are running very simple contracts. And this is essentially benchmarking the startup time of these contracts. So another important factor is like making sure that a lot of these smart contract programs are very short-lived. They need to start up quickly because they don't actually perform that much work. And having like a large startup time would dwarf the cost of the overall contract. Um, and then also, with Groundhog in particular, we want to make sure that there's no scalability problem with spawning many sandboxes at once. Um, so here, the dash line is if we provide like the cryptographic routines that these smart contracts are using as runtime calls. So they're implemented as native code that the sandbox calls out to. And then the solid line is if the cryptography is actually performed in the sandbox. So with Deco, we lose a lot less performance when we put the crypto in the sandbox because the sandbox is able to execute at closer to native speeds than with a WebAssembly approach. With WASM 3, you can see like if the cryptography is in the sandbox or is provided by the runtime, WASM 3 is quite performant. It has good startup time and everything. But if it has to do the cryptography in the sandbox, all of a sudden it's like down here at the bottom because the WASM execution environment is so slow. And so if you ever have to like do some cryptography that's not provided by your runtime API, you're in trouble when you use this interpreter environment. So that's the conclusion. When we try to put replicated state machines together with extensibility and we want maximum performance, you get something that looks like deterministic client. I've got the artifact in the paper linked from here. And yeah, that's it. I'm happy to take questions. Thanks.
Thank you, Zach. Wow, that was awesome. Um, I have a couple
Good
like
job, Zach.
can you hear? Yes, good job, Zach. I have a couple high level questions, and uh, I also want to open it up for Paul or David or Pitar if they have any questions or follow up. I'll start. Okay, so uh, do you see um, like I guess part of this research is looking at determinism as kind of like as it's tied to trust. And so I guess my question is, um, should we think of determinism as like a fundamental property of trust within a blockchain, or like how have you kind of reflected on that through your work here?
Mhm. Yeah, I mean, I think, yeah, like determinism, in terms of sandboxing, there's a lot of properties that might be interesting to enforce on programs. And typically that's like memory isolation is the classic thing that, the sandboxing research community has tried to enforce on programs. But I think definitely like in terms of blockchain, determinism is like another one of the fundamental properties that we want. And so that's led to like more sandboxing systems where we want to try to enforce determinism and thinking about how we can use the existing mechanisms to enforce that property, I think is interesting. Like I think determinism is a property where basically only software-based techniques work. Or for memory isolation, the hardware can provide a lot of um, mechanisms for preventing loads and stores from accessing unwanted data. But current CPUs, and really it's difficult in general for the CPU to like provide um, a hardware-based form of deterministic sandboxing. So yeah, I think like it's interesting that yeah, determinism is I think definitely like a fundamental property of the trust of smart contracts, and then we also need to it's like required to use software-based techniques to enforce that.
Sure. Yeah, that makes sense. Um, okay. Anyone else before I go with another one?
Qatar. Oh,
I mean,
oh,
and I was just gonna say, I mean, it's such a nice talk that it's a little hard to like have. Um, I mean, it was very clear, so that I don't actually have technical questions on the talk. I basically the only questions I can think of asking is like, is there like what's the future direction? Because this seems like a complete piece of research. Like it probably couldn't squeeze more performance out of this technique. And the other question I had is, I can't like make it out in my head quickly enough whether there's anything to be gained from the kind of non-determinism that groundhog allows, basically.
Hmm.
Um,
Yeah, so for future direction, yeah, I think like in terms of squeezing out more performance, I think it's roughly yeah, it's sort of close to the limit, I would say. In terms of like things that would make it practical for adoption, in terms of future directions, I think there could be more along that line in terms of thinking about some of the portability problems that the technique imposes, limiting you to a single architecture, and then also sort of it becomes difficult to update the smart contracts. You have less flexibility in terms of your like execution engine because now your smart contracts are you really just want to be running them bare metal. You don't want to be running like an additional layer of indirection in between. And so if there's like something like there's a hardware bug that you discover that actually has some non-determinism and you want to try to resolve that, that becomes more difficult. And I think there are some interesting directions in terms of maybe targeted, lightweight rewriting of the program. So sort of a JIT that can target specific locations or something like that to address some of those limitations. And then also like for portability, I think there are some ideas that I have about doing determinism in a way that's similar to this, but can also apply to across architectures, where like maybe you have a verifier that can verify like across the two programs the equivalence of the determinism. Anyway, I think those are some interesting future directions. For groundhog, I think I'm unfortunately not familiar enough with the non-determinism that it allows to be able to say really like uh, whether there's some additional performance that could be squeezed out by taking advantage of that. Yeah.
so
thank you.
I have a question, which is is the LLVM stuff like how useful is that for if you care about determinism? Like, does
Yeah,
it?
I think like so like you mean the stuff that's actually going into LLVM.
Yeah, in
Um,
other words, would you still to do decal? Would you still just do it as a raw part pass on the assembly language, or would it be useful to kind of first do the LLVM stuff and then do another pass?
Yeah. So certainly like the like decal without the preemption is actually almost like for ARM, it's basically exactly the same as just normal LFI. Uh, because all you're doing is like you just have an additional verifier that's restricting you to the subset. And maybe restricting additional more instructions than usual. But the compiler itself is basically the same in that case. And so like the things that are going to LLVM can also like you could reuse that same compiler just with a more strict verifier. On the x86 side, there's these additional problems with like shift instructions. There's a couple and like the flags. Again, the flag stuff is not really a compiler modification that has to be made. It's just a verifier modification. With the shift instructions, there's a few rewrites there that need to be performed at the compiler level. But I think it also those types of rewrites can reuse a lot of the same infrastructure that we're building out for assembly rewriting in LLVM. So it becomes a lot simpler uh, to like modify the assembly rewriting pass, or if you wanted to continue to use my like the external rewriter approach that I was using in this project, you can do the existing rewrites that are going to be shipped in LLVM, and then do some external rewrites just on top of those at the end to support DECL. And I think so I think that it does like reduce the amount of complexity that you need to like maintain outside of LLVM to do the DECL rewrites, even though what's going into LLVM is not fully DECL, it's the LFI stuff, but that actually provides a lot of the rewrites that you would want. Uh, on the ARM side for preemption, we did use bundles as well. And that bundling as a general thing has been removed from LLVM, and we're putting it back for LFI, but only in the x86 portion of LLVM. And so that would require some more effort, I think, to either maintain bundling in the ARM backend as well, or use a different approach for the control flow.
But
Yeah.
GCC still has bundling, or GCC
GCC does
never?
still have bundling. Yeah.
Yeah, okay.
Okay, great. Uh, well, I have one more kind of high level question, and then maybe I'll just also ask you to close um, with a little bit of comments on new research you're looking at or like other projects you're looking at outside of this. I think people are probably interested, but so, um, in general, blockchains rely on like constrained machines for their like to ensure safety and for their operations. So do you like if people were starting to execute this near native code and like using your solutions, does that like reframe how they should be thinking about blockchain architecture? I mean, maybe this is also a question for David, but um, yeah, does kind of like does this new technology have any implications for how blockchain architecture is developed or how it works?
Yeah, I guess maybe it reframes it a little bit in the sense that like you start to think of the programs that you run on blockchains less like just sort of small like these small programs that you've just like tuned for specifically to run the blockchain system, and there's like more ability to run like your general purpose programs. You're going to be using like your normal LLVM compiler and your normal development tools with like it's just like ELF files and stuff like that. And so it sort of moves you more towards a situation where like the blockchain programming environment is just sort of the same or very more similar to a typical programming environment for just for native programs.
Hmm, interesting. Okay, and then anything that you're researching right now or any new projects you want to highlight? If I'm sure if folks are interested in this research, they're going to want to know a little bit more about you.
Yeah. I guess one thing that I've been sort of thinking about lately is, I've done a lot of this work on sort of coarse-grained sandboxing, where you're compiling your code to run to just give it like a 4 GB region that it can have access to, and it can sort of do whatever it wants within that within and it's sandboxed just via this like verifier. I think I'm also interested now in like looking at more fine-grained things, specifically like things sort of like Rust, but where it's actually like malicious, like it's an adversarially enforced sandbox where you have like you can share buffers directly with it. You don't. It's not like you're just giving it this 4 GB region within which it can do everything. Instead, you're like you have some more fine-grained control, but it's still a malicious program. And so you can do some sharing, but you're still wanting to make sure that like the compiler is not a trusted component of the system. And so maybe you can compile down to an assembly language that is linearly typed and has similar guarantees to Rust, but the type checker, because maybe it won't have generics, or a lot of the language will have been lowered before it reaches this typed assembly language, low level typed assembly language. Then the type checker for that will be a lot simpler and a lot more trustworthy. So that's sort of the direction that I'm looking into. Uh, I think there's other directions in terms of also the just for LFI, the practicality of doing the instrumentation and performing these rewrites. I have some ideas for how to do this instrumentation on binaries rather than doing it directly in the compiler. So like some compiler modifications that allow you to do arbitrary instrumentation of the binary after the fact. Yeah, those are my two projects.
Um, just another question I had. Is it fair to say that right now the sort of like the biggest application is basically doing cryptography in a deterministic on blockchains basically?
Yeah, for deterministic client, I think the main thing, like the main CPU bound algorithms that people want to run inside of smart contracts are these heavy cryptography things. Yeah.
Mhm. One more question. So I'm just curious. So imagine you have like a normal blockchain like ours already built, and you want to offload the cryptography calls um, to a sandbox like the one that you're describing. I wonder if there's any techniques to make the offloading essentially secure and deterministic. I mean, this is kind of like an open-ended question. In the same, I mean, a parallel, I guess, to my question is, um, and David, maybe you can tell me too, like if you had like a secure enclave and you wanted to send the computation from a blockchain to a secure enclave, can you make it in a way that you have a guarantee that the computation was not messed with? And then could you do the same thing with Zach's technology, basically, or similar thing? You see what I'm saying?
You're talking about combining them or using them
No, no. So
as
let's say you have an existing blockchain and you want to be able to benefit from Zach's technology. You're not going to change the blockchain, but maybe you want to like send some contracts or some functions to be executed in his environment, in the sandbox
you can
environment.
extend it. You can say like there's a new transaction type which is like a native transaction
Yeah,
type.
yeah.
Likewise. Yeah.
But it should be able to be called as a subroutine in a normal transaction as well, though. Like that's what I'm trying to get at. Would that be? That doesn't seem. Maybe that's completely straightforward. Because it would require the WASM to call into a sandbox. Is that like link decent?
Yeah, I mean,
So
maybe the WASM contract could provide like these sort of native code plugin things that would run in like a DECL sandbox. And then,
hmm,
um, yeah, I mean,
okay. Okay, I guess that's pretty. I guess that's actually straightforward. I mean, it seems like okay, cool. Thank you.
Awesome. Well, I think we will go ahead and wrap this up. Thank you so much, Zach. This was a great talk.
Thanks.
I'm excited to share the video. And anything anybody else wants to say, David?
Well, thanks. Thanks for watching. Thanks anyone for watching the video also. And yeah.
yeah, all right. Thank you.
All right. Take care,
Bye.
guys. Bye.